Good evening, everyone. Welcome to live session 4 of Mechanics of Material. My name is Vaibhav Gupta, and today I'll be covering the topics covered in week 4 of Mechanics of Material, and I'll be solving some problems, hands-on problem with you. So, first of all, this is a problem we'll be solving later in this lecture. First, I'll cover the summary of lecture 4, what has been covered so far. Okay. Am I audible?
Yes, sir.
Okay. So in week 4, what was covered? So basically, the topic chain is covered in week 4. So before moving to the strain, we need to understand few things. Okay. So I won't give you some inside things into detailed things, but I'll be covering some like important formulas which will be used and help you in solving the problem of week 4. Okay. So the first main thing which was covered there was deformation gradient. So it is denoted by F double dash. Okay. So why double dash? Because F is a second order tensor. So what is F? F is nothing but partial derivative of position vector. Basically, F is a second order tensor which maps two different tangent lines. Okay, from current to reference. It has been covered in the lecture. So in the matrix, how we'll write this thing? Why I am writing small x and capital X? Can you tell me?
Yes, sir.
Why?
Current coefficient and reference coefficient.
Not coefficient. Reference
Oh,
position
reference
vectors. Okay.
point.
So
Okay.
small x, small y represents all the current configuration. Okay. Particles present in a current configuration. Okay. And capital X, capital Y, capital Z, these are known as reference configuration. Okay.
Okay, sir.
So I'll just complete this formula. So this is deformation gradient F. Okay, it's a partial derivative of the position vectors. Okay, why I am focusing on position vectors? Because one more term I'll be discussing is displacement gradient. So both are different. Displacement gradient and deformation gradient both are different. Okay, displacement gradient is a partial derivative of the displacement vector u. Okay, I'll cover now only. So this is F. So what is the property of F? Property of F is that F inverse is equal to identity matrix. Okay. So remember all these properties also. Okay, it will help you in solving the questions. Okay. Second thing covered was, which was I was talking just now, is displacement gradient. Okay. So this displacement gradient is nothing but grad of u. Okay. This is nothing but partial derivative of u means displacement. So in this two terms will come. See, you have seen in previous lectures that u is nothing but small x minus capital X. Okay. And we can define u in two things, material form as well as spatial form. Correct?
Yes, sir.
So when I write u small x, what it will represent? It will represent spatial form. And if I write U in terms of capital X, what will it represent?
Material form.
Material form. So now what I'll be doing is that whenever I will write capital G, grad U, it represents I am taking displacement gradient in material form. Okay. This is what notation follows in the lectures also. So this is a partial derivative of the displacement in the material form. Okay. So how you will write in matrix form this thing? So far understood?
Yes, sir.
Okay. So this all things will be clear with the help of example. First I'll tell you what are the concepts I am using today, okay, and what has been covered in the lecture week 4. Okay. Similarly, this is known as capital H. Okay. And similarly, small h is equal to grad of U, but which is a partial derivative of displacement in spatial form. But okay.
Sir, what is the difference between capital and small h?
See, capital H is the displacement gradient of the displacement vector in material form. See, in this form.
Okay, sir. Okay, sir.
And small h is the partial derivative of the displacement in the spatial form. Got it?
Yes.
We'll solve one example and see. Okay.
Yes, sir.
All these things will be clear. So I'll write this for the completion. This thing. See, that's why I'm using small x, small y also, so that you won't confuse. Okay, this is the displacement gradient. Okay, see, deformation gradient and displacement gradient both are different. Don't confuse in these two things. Fine.
Okay, sir.
Okay, next we studied in week 4 what is stretch ratio. Okay, it is denoted by lambda. A is the unit vector or position vector, and it is defined as the ratio of current length by original length. Okay.
Okay, sir.
I won't go much deeper in these things. All the derived, sir has derived all the things in the week 4 lecture. If you have doubt, I will show you. Okay. This thing. So, this in the simpler way, we can write this thing as in this thing. Okay. What is dou ux by dou x? Just now I told you. This is nothing but displacement gradient. Okay. In material form. Okay. And the strain is defined as nothing but epsilon. Change in length by original length. Okay, this is one of the type of strain. Okay. So here next thing comes is right Cauchy Green deformation tensor. This is denoted by C, and the formula to get the value of C is this, F transpose F. Okay. Also, F transpose F is not equal to F transpose. Okay, so don't merge these two things. Okay. So these are the formulas that has been covered. There are some other formulas, but I think like with the help of example, you will be get to know that thing clear. Okay. So see, in the week 4 lectures, two things are very important: small deformations and large deformations.
सर ये F इनवर्स लिखे हैं आप?
No, F transpose T.
Okay.
Okay. So C is equal to F transpose F, and F transpose F is not equal to FF transpose. Okay, both are different things.
Okay.
Okay, in the future lectures you will be dealing with FF transpose also. But right now, as per peak 4, C is equal to F transpose F. Okay.
Okay, sir.
So now two things are there: small deformations and large deformations. Okay. If you have gone through week 4 lectures, you have heard like if the magnitude of something has to the order of 10 to the power minus 3, then we will neglect something. Okay.
Yes, sir.
So how these things are coming into the picture and how we have to solve the problem by looking at these things, I will tell you now. Okay. So directly I'll move with the example so that it will help you. Okay.
Yes, sir.
So I have made one question. So just go through this question once. Take 2 minutes and read the question. A body in the form of a unit cube given by B in the reference configuration is subjected to the following deformation field. The same example we have solved in previous problem solving session also. Okay. So here A is a constant and capital X, capital Y, capital Z are the Cartesian coordinates of a material point in the reference configuration, and small x, small y and small z are the Cartesian coordinates of the same material point in the current configuration. Okay. So first I'll write a deformation field. Okay. What is given to us? Okay. So, 1 second. Okay. So, problem. Okay. So, deformation field. It is given. Okay. So, small x is equal to 1 plus a into capital X. If small y is equal to capital Y plus a capital X, and small z is equal to capital Z. This is what given to us in the question. Okay.
Yes, sir.
And what they have asked? Determine the displacement vector components in both in spatial form.
Okay.
Okay. Can you calculate?
Yes, sir.
I will also calculate with you. Okay. So we'll check the answer then. So they are asking first U capital X. Okay. Which is as per the formula is small x minus capital X. But in material form, what variable we need to shift or change? Small x, because we have to find in material form.
Yes, sir.
So just change small x to capital X, capital form. So this is nothing but this. Small y will be equal to nothing but this. And small z is this.
Yes, sir.
Minus capital X, capital Y, capital Z.
Capital Z.
So ux becomes ax 0.
Yes, sir. Yes, sir.
Got it?
Yes, sir.
This is in material form. Second, they have asked in the question u small x in spatial form. Same formula, but now which variable we will change? Small x or capital X?
Sir, एक minute. Sir, small x.
No, small x will change in material form. We'll convert small x to capital values. Just now here we change small to capital, no? This small thing We have changed to capital. See, are you getting it, or shall I explain in another way?
Sir, explain,
Okay.
sir.
See, in material form, we just first check the deformation field. So, see, here relation between current and reference configuration are given. Here small x, small y, small z are current configuration. Okay. In capital X, capital Y, and capital Z are in reference configuration. Okay. So now they are asking to tell the displacement in material form. Material form nothing but is a reference form. Okay. So when you find something in reference, you have to change another thing into reference only. Then only you can compare mangoes and mangoes. Just like
Yes, sir. Yes, sir.
so here the displacement is nothing but small x minus capital X. And you have to find the answer in reference configuration. So which variable you will change, small x or capital X?
Sir, capital.
No, capital is in reference only.
Small, sir. मतलब current configuration.
Yeah. See, you have to find the answer in reference only. So which variable you will change? Current reference wala, current configuration or reference configuration?
Sir,
you have to change the current configuration to reference configuration.
Yes, sir.
Okay, that's why we have changed small x. We have converted the small variables to capital. So
yes, sir.
the first element is this only. Got it?
Yes,
second
sir.
is this.
This.
Got it?
Yes,
and third is this. Got it now?
Yes, sir.
So in material form, ux is this. Got it?
Yes, sir.
So now in spatial form, see, this is in current, this is in reference, and we have to find ux in current or spatial. Current or spatial are same words, okay? So which variable you will change? Small x or capital X?
Small x.
This you will change or this you will change?
Yes.
Small x you will change?
Yes, sir.
No. Again wrong. See, right hand side current. So left hand side should be in current now.
Yes,
Suppose
sir. Yes, sir.
U is your mango. So current is also mango. And this is orange.
Yes,
so can you subtract mango with orange? You have to first convert the orange into mango, no?
Yes, sir.
Got the point?
Yes, sir.
So what will you convert here?
Sir,
Capital X
here
to
reference.
so reference to current. Okay.
Yes, sir. Yes,
So
sir.
now capital X is equal to small x upon 1 plus a. Capital Y is equal to
small y upon
minus a capital X, and capital X is this. So what it will become? Okay.
upon 1 plus a.
And this will be this. Got it?
Yes, sir.
So now right here. See, this is the basic step. Every problem you have to go by this method only. Okay. So if you are not clear, you can ask me any number of times. Sir. In exam also this will come. This type of things. Okay.
Yes, sir.
So now we'll subtract. Till now you are clear now?
Yes, sir.
So if you subtract, what you will get? This you will get if you subtract. Okay.
Yes, sir.
So now you have find out the displacement vectors. Okay. Now second thing you have to find out is deformation gradient. So just now I have told you what is F. Okay, this is the formula to calculate F. Okay, so what is the deformation field given? So what is the value of F you will get? Tell me.
सर
हाँ,
मैं अभी पिछला क्वेश्चन करा था तो उसमें जो x रहेगा वो x अपन 1 + a ही हो जाएगा.
see this x minus x upon 1 plus a. What you will do? What you will get?
माइनस करने पे
See, this is x minus x upon 1 plus a, which will be 1 plus a into small x minus on 1 plus a. Okay.
यस सर.
So what is become ax upon 1 plus a? Got it?
ओके.
Got it? So next part, deformation gradient. So the deformation gradient is nothing but partial derivative of current with respect to the reference. Okay. So if you do the partial derivative of small x with respect to capital X, what you will get? 1 plus a you will get.
यस सर.
What is this term you will get? This term?
दिस टर्म सर dx अपन dy.
D small x upon D capital Y. This thing is for your clear.
कैपिटल. ओके सर.
So this derivative of this with respect to capital Y, it is nothing but 0. No capital Y term is there. What is the third? Dou small
Zero.
x upon dou capital Z? 0.
0.
What is this? Dou small y by dou capital X?
सर y + a.
No. Small y with respect to capital X. Only derivate the x term. Now it will derivate the x term.
ये यस सर. यस.
A. Okay.
यस सर.
What is dou small y by capital Y?
ax.
No. Only it will derivate y term. Capital Y term. Partial derivative means it will only derivate that terms which contain that variable.
Okay. Okay.
Suppose in this I will explain. It will derivate capital Z term in the small y equation. Okay.
Yes sir.
It will derivate capital Z term in a small y equation. Okay. So in this small y equation, capital Z term is there or not? No.
No sir.
So derivation is 0. Now come dou small z by dou capital X. So in this thing, it will derivate capital X term in small z equation. So no x term 0.
No sir.
Similarly, no y term 0. And here 1.
Here 1. Yes sir.
So you got it how to calculate F deformation gradient?
Yes sir. Yes sir.
Clear?
Yes sir.
Okay. Okay. So now we'll go to next point. Displacement gradient. So just now we found out U capital X and U small x, these things. Okay. We write here U capital X is nothing but AX 0. And I told you just in the starting of this class, capital H is equal to dou U capital X by dou capital X.
Capital X.
This is nothing but displacement gradient in material form. Okay. This is nothing but displacement gradient in material form. Okay. What is the formula for this? Dou U Are you able to understand till now?
Yes, sir.
Okay. Okay, this is the formula. So now, what does this first term means?
First term means, sir,
Derivation of capital X term in UX equation. This is UX, this is UY, this is
and
UZ. Okay.
Yes, sir.
So what is your H? This first term becomes
1.
no A. Derivation of X. Okay.
Yes,
This
sir.
becomes derivation
0.
of Y term in UX. 0. Good.
0.
What this becomes? This becomes
0.
0. Correct. Now you got it. What this term becomes?
UI in term of A.
You have to find the derivative of capital X in UY term.
UI term.
So
that is 1.
No A. See, in UY term, what is there? AX. Okay. So you have to derivate X here. What will be the answer you will get? A. Here, UY derivate 0. Good. Here
0.
Okay, good. This term
0, 0, 0.
yes 0 0 0. Okay.
Okay.
So this is a capital H displacement gradient in material form. Okay. One more formula is there to calculate H. See, this H is nothing but dou ux by dou capex, capital X. Okay. You know ux is small x minus capital X. If you differentiate this thing, what you will get? -1. 1 is nothing but identity matrix. This you will get.
Yes,
if you differentiate this thing. So what is this thing? This is nothing but your deformation gradient. So your H will become H minus identity matrix. Okay. So initially we have found out F also, this F. Okay. This we have found out.
What, sir?
See, I have told you H is nothing but partial derivative of Ux with respect to capital X. Okay.
Yes, sir.
Now we write Ux in terms of small x minus capital X. So now if you derivate this thing, you will get this expression.
Yes, sir.
And this expression is nothing but deformation gradient. And deformation gradient, we have found out this initially.
Yes, sir.
So we will check our answer is correct or not. So H is equal to what is F? F is 1 plus A 0 0
0, 0, 0.
A 0 no sorry 1 0 0 0 0. This is see this F and this F same. Okay. Minus identity matrix. Okay. What you will get H?
H is equal to 1 plus A.
A 0 0 A 0 0 0 0. See here 1 is there. I left. Okay. So now see this red H and this green H both are same.
Yes, sir.
So one way to find H is directly you find Ux and you derivate. Okay.
Yes,
with the help of this formula. And one way is if you find out deformation gradient F here, you simply just do this thing F minus identity matrix. Okay. Got the point?
Yes, sir.
So similarly now we'll find small h. What is small h? Displacement gradient in spatial form. Okay,
Yes, sir.
now our u small x is nothing but a upon 1 plus a. This is what we have found out.
Yes, sir.
So now dou u small x by dou small x will be equal to,
Dou u small x
I'll just
upon
write the formula first, then you see and tell me the
सर
answer.
ये जो ऊपर कैपिटल एच में लिख रहे थे आप,
Yes,
उसमें वो डेल यू कैपिटल एक्स था कि स्मॉल एक्स था?
capital X. See, capital, if I am finding out anything capital, I will use always capital thing. Okay,
ओके सर.
this
हमारी
this capital as I am finding out, then dou u capital X. Okay, small x I will make like this. Okay,
ओके सर.
so this is the formula. So now we have to find out what is this term. Derivation of small x in u small x term. So what is the answer?
ए
What is
1 प्लस ए
very good? What is second term?
0
0. What is third term?
0.
0. Correct. What is this term?
दिस टर्म सर
Derivation of small x
A.
present in.
हाँ यस सर, स्मॉल वाई ए 1 प्लस ए
Correct.
0 0.
Very good. Last one is 0 0 0. Okay.
Yes
This
sir.
is small h. Okay. You got it.
Yes sir.
Similarly, see, h is equal to f minus I. Okay. We saw small h is nothing but I minus f inverse. Okay. Okay. The
Yes, sir.
formula to find h in terms of deformation gradient matrix is this. See, finding inverse of a matrix is difficult. Okay. In exam also, to find inverse is difficult. Okay. So you can go through with this computation also. Okay. How we are finding like this. Okay. But something is not given and only f is given. Then you have to find out this thing. Okay. So you can either find h with the help of this matrix, or you can find h with the help of deformation gradient. Okay, if I do the inverse of f, it is nothing but, I will write what is the f inverse. So this is the f inverse. Okay. So now h is nothing but I is 1 0 0 0 1 0 0 0 1 minus,
minus f inverse.
yes. If you will do, what you will get?
1 upon a 1 plus a. सर वो a है ना?
Yes.
Yes sir.
Got it.
Yes sir.
So you can see this h and this h both are same.
Yes sir.
So I'll write two statements. When u is given, okay, u means displacement vector. Okay, h is equal to dou u capital X upon dou capital X,
Capital X.
and small h is equal to,
दो small x upon small x.
okay. And when deformation gradient is given, See, you can find deformation gradient from above also, but just for the simplicity, I am telling you, okay, so that you can remember these things. Capital H is nothing but F minus identity matrix, and small h is nothing but, okay, you can find out with this also, okay. So now you know how to calculate F also. F, okay, and you know now how to calculate H and small h also. Yeah,
तो थोड़ा सा स्लाइड ऊपर करें.
yeah, this slide.
थोड़ा नहीं सर, वो फार्मूला जो था एफ इनवर्स अपन एच, वो फार्मूला लिखना था.
This is F.
ये नहीं सर, वो नीचे वाला.
This, oh, last one, huh?
लास्ट. ये सर थोड़ा सा ऊपर. ये सर वेन एफ डिफॉर्मेशन.
Okay.
H is equal to F minus 1.
1 means identity matrix, okay? Don't
Yes,
write
yes,
put simply minus 1, okay?
Sir.
Okay.
Thank you, sir.
Okay, so till now you understood what I am doing?
Yes, sir.
So just summary of all these things, then I go ahead. See, deformation field is given to us. Okay. Is given. What is given? 1 plus a into capital X, small y is equal to capital Y plus a capital X, and small z is equal to capital Z. This is given. Okay. So first, what we found out? U capital X. Displacement vector in material form. Okay. This we found out. Okay. Then we found out U is small x.
Small x.
Displacement vector in current form. Okay. Next we found out F, which is dou small x by dou capital X vector. Okay.
सर ये एफ
या
सारे क्वेश्चन में एफ निकलना जरूरी है कि वो तो पूछेगा ना कि फाइन.
See, F is important. Why? I will tell you in, like, we'll move forward. As we move forward, F is required in all the things. Okay. So you have
सर
to find
क्या
out
लिखा
F.
रहेगा कि हम
I'll tell you. We'll solve more examples, so you will get to know. Okay. Then we found out capital H, which is nothing but partial derivative of displacement vector in material form, and we calculated small h. Okay. Also we saw capital H is nothing but F minus identity matrix, small h is I minus F inverse matrix. Okay.
Yes, sir.
So far we have seen this thing. If you have any doubt in this thing, like you have any doubt, or all things are clear?
Yes, sir.
So now next we move forward. Okay. So now I will define strain, linearized strain. Okay. So epsilon is nothing but half of H plus H transpose. Okay. I will tell you one more thing. See, I have told you the property of F inverse to be equal to identity matrix. This is the property of F. Okay. Now you know F is nothing but H plus I. From here, you can do like this.
Yes, sir.
And F inverse is nothing but 1 minus small h.
Yes, sir.
Which is equal to this. If we open this thing, what we will get? H plus I minus small h minus
yes.
This is equal to I. This will cancel out this.
Yes, sir.
So what left?
Small h minus.
This is left.
Yes, sir.
So see, in the lecture you have seen order 10 to the power minus 3. If the order of h is 10 to the power minus 3, small h also. So when you multiply this 2, it will 10 to the minus 6, 10 to the power
Yes.
minus 6.
Yes, sir.
So this is very small.
Yes, sir.
So this goes to 0. If it's very small, it is negligible, it's 0 only.
Yes.
So
Yes, sir. Yes, sir.
capital H becomes small h. So when we talk about linearized strain, it means you can write this thing either in spatial form or material form. Both things are equal. Okay. Okay. I can write strain as half of h small h plus small h transpose also. You're getting my point?
Yes, sir.
So why this order comes into the picture is when the order is small. No matter whether you're writing in material form or spatial form. You're getting it?
Okay, sir.
So you can write in either form. So in this problem, I will focus on material form only. But you can write in spatial form also. You can check in your home. I will just do 1-2 calculation to tell you like why these are same. Okay.
Okay, sir.
This thing you got it.
Yes, sir.
So you can calculate strain also. What is our H matrix there? I'll write here. 1 second. So strain matrix is nothing but half of H. H is capital H. A00, A00, 000.
0.
Okay. Plus H transpose.
A 0 0 0 0 0 0 0.
Correct?
Yes, sir.
So epsilon will become, if you do plus addition,
2
A by 2.
A by 2. Yes, sir.
2A divided by 2 is A only. Okay. Got it? Or doubt?
No, sir. Got it.
So this is strain. So to find strain, you have to find out capital H. Okay. And to find out capital H, you have to find out either deformation gradient F or you have to differentiate partially the displacement vector. Now you
Sir,
got why you want deformation gradient every time.
Deformation gradient.
See, to find epsilon, you have to find out H.
Yes, sir.
Which is nothing but
du. Yes, sir.
or.
F.
So you have to find out this also. That's why you find these things. Okay. I have answered your question you have asked. Why you have to find out deformation gradient every time. Okay. Understood?
सर ये आप अभी स्ट्रेस निकालें कि स्ट्रेन निकालें?
Strain. See, okay. Stress is sigma. This thing is stress.
ओके सर, बस आप फार्मूला पे रख के उसको पुट किए, मतलब वो हाफ S plus H transport.
Yes.
Okay, sir.
Only I put the formula. Okay. Yes. And why I have used this formula? I have told you why this order terms come here. Okay. What is the meaning of order? Okay. So moving next.
सर लेकिन हम A और A को जोड़ेंगे तो 2A होगा ना?
Yes. Then 1/2 is also outside ना?
Oh, sorry sir.
Yeah. Till now clear?
Yes sir.
Now I have told you about C matrix also. C is nothing but F transpose F. This is called as green. Right, green 40 tensor. Second order tensor. Second order deformation tensor. Okay.
Yes sir.
So one formula to find C is this, and another formula to find C is 1 plus 2 epsilon. Okay. I will not go to detailed derivation that how I am getting 1 plus 2 epsilon, or I'll show you. 1 second. See, F is identity plus H.
Yes,
Okay.
sir.
So what is C? F transpose. F transpose is H transpose. I transpose is I only, and I plus H. Okay. So if you multiply this, you will get H plus I plus H transpose H. This you will get. Are you with me?
Yes, sir.
See, formula of C is this.
Yes, sir.
F we define like this. We have seen
Yes, sir.
here. You have seen here this thing.
Yes, sir.
So if you put this thing, F transpose F. So transpose of this is F transpose is I plus H transpose. Transpose of I is I only plus H transpose. Okay.
Yes, sir.
This I have put it here only. Okay. Multiply by F. So now see order terms. If order is 10 to the power minus 3 again, this becomes 0.
0.
So what left? 1 plus H transpose. And we have seen before, like, what is strain? Strain is half of this.
Half of this.
So H plus H transpose is nothing but 1 plus 2 epsilon. Got it?
Okay.
How we got this thing?
Yes, sir.
So to calculate C, we have two things. Either you do F transpose F, because you have calculated F matrix also, or you calculate this thing. So when to use when? Okay. See, here in this formula we have used assumption that order is 10 to the power minus 3. Okay. It means small deformation. Okay. So by chance in question, if they ask large deformation, okay, I'll show you the example also. So you don't have to use this formula. You have to use this formula. Okay.
This formula. Yes, sir.
So I'll show you, like, see, our F matrix is as per our question 1 plus A, A 0, A 1 0 0 0 1. I'll just confirm above, but this is, where is F? One second. 1 plus A 0 0 A 1 0 1 plus A 0. Okay, 1 plus A 0 0. So this is 0. Okay, this is our F matrix. Okay. And what is our epsilon? Just now we have calculated A by 2 0, A by 2 0 0 0 0 0. This is epsilon. Okay.
Yes.
Now first I will calculate C with F transpose F. Okay. So what is F transpose?
F transpose, sir, A plus
This multiply by F. If you multiply these two things, what you will get?
whole square.
A square
Plus
A 0. This you will get. Okay. And if I open this thing, first term, you will get 1 plus 2A plus 2A square. Okay. And if I will calculate C with this, what you will get here? I multiplied 2 also, okay, inside this epsilon.
Hmm.
So what you will get, C? 1 plus 2a.
1
A.
plus A.
This you will get.
Yes, sir.
Now you tell me, is this and this are same?
No, sir.
1 and 2. 1 and 2 are not same.
Not same.
But I said that we can calculate C with using these two formula.
Hmm.
So see, here A term is there, no? Here in this one equation.
Hmm.
If I say A has an order of 10 to the power minus 3.
Yes, sir.
So this A square becomes 10 to the power minus 9.
6. Yes, sir. Yes, sir.
So this becomes 0.
Hmm.
So what left? 1 plus 2A only.
2A.
Other terms are not A square.
Hmm.
So now this and this becomes same. 1
Same.
and 2.
No, sir.
Why? Which term is different?
सर नहीं तो सर अगर a इक्वल टू -3 रहेगा तो सर 2a पे तो भी a इक्वल टू
No, see, 10 to the power minus 3 multiplied by some value which is like not point is reasonable. But if you are saying like square, it becomes 2 less. Okay.
केवल
Like
अगर
2 into 10 to the minus 3 or 5 into 10 to the minus 3, these are reasonable. But if you say I am just adding 10 to the power minus 3 with 10 to the power minus 6 or 10 to the power minus 5, these are not same. Okay.
ओके सर मैं बस यही पूछना चाह रहा हूँ कि अगर केवल मतलब 2a है तो यहाँ 10 to the -3 जो है 2a पे वैलिड है कि नहीं वैलिड?
Yes, it's valid until it's not going towards 10 to the power minus 5. It's not decreasing.
Okay.
See, multiplying with some greater number will increase the value, no? See, 2a is greater than a only, no? So why we will neglect? But a square is smaller than a.
Yes, sir.
You are getting the point?
Yes, sir.
So we will neglect this value, but we will not neglect this value. You are getting the point?
Yes, sir.
See, 10 to the power minus 3 is smaller than 2 into 10 to the power minus 3. But 10 to the power minus is greater than 10 to the power minus 9.
Yes.
You are getting it?
Yes, sir.
So this is what the reason of neglecting. Okay. See, the main point is, which I was telling you, see, these two C1 and 2 equation were not same as per our question. Okay. If I assume the value of A to be the order of 10 to the power minus 3, a small value. So this 2a square term will goes down to 0.
Yes, sir.
So now this equation 1 and 2 become same.
Yes, sir.
So that's the answer also. Like if small deformations are given, C can be equal to F transpose F as well as equal to 1 plus 2 epsilon. Okay. Both are valid. And for large deformation means order is greater than 10 to the power minus 3. Okay. It will be mentioned in the question only. You don't have to worry.
Okay, sir.
Whether deformation are large or small. C is equal to F transpose F. Okay. Just make sure this thing. Okay. Got it?
Yes, sir.
Now clear what is the difference between order thing. I have told you with the help of example also.
Yes,
okay.
Sir.
So now you can calculate C also. Okay. Why we want C? We'll see now. See, now we have to find the change in length. Okay. Okay, change in length. Change in length is nothing but lambda n minus 1, which is nothing but root of C n dotted with n minus 1. Okay. Okay.
Yes, sir.
So simple form is when deformations are small, the value will be equal to epsilon n dotted with m for small deformations. Now you know why I am writing small. Because
Yes,
if deformation not small, you cannot use this epsilon. You have to go by this method, C n dotted with n, where C is calculated with the help of this thing. Okay. Okay. I am saying my deformation is small. You can use this thing. Okay. Suppose in the question now, in the given question, I'll show you. This is a question given. E part. Using the linearized material strain. Okay. One more thing you will tell me. Material strain will be equal to spatial strain or not?
material strength will be
For small deformation.
small deformation.
See, both are same. Okay. I told you no that capital H becomes equal to small h when order is 10 to the power minus 3.
Yeah.
Got it? So either you write strain is equal to half of capital H plus capital H transpose, or you will write half of small h plus small h transpose. Both are same. Okay. Okay. So material strain is equal to spatial strain. Okay. Got it?
Yes, sir.
So now moving ahead with E part. Using the linearized material strain, calculate the exact change in the angle between two line segments oriented along EX and EY direction. Okay. So now they have given like change in angle. Okay, we have to find change in length. We have to go for first. We have to solve F part. Sorry. So F part is using the linearized material strain, calculate the exact change in length of the straight line. First EX. Okay, along the direction EX. Okay. So in first question they have said change in length you have to find out. Okay, in EX direction. Okay. So epsilon matrix we have calculated, which is nothing but A by 2 0 A by 2 0 0 0 0 0. Okay. And they have given EX. Okay. So what to do now? Just multiply.
सर EX जो है वो n
Yes.
n ले लेंगे.
Yes. It's a vector. Okay.
Okay, sir.
This n is a unit vector. So what is x? 1 0 0 EX dotted with 1 0 0. Okay. Understood till now?
Yes, sir.
So first we'll multiply these two things. Okay. Don't directly dot product. Okay. Don't do this thing first. Dot product. Okay. First you have to do this thing. So what you will get? A
by 2.
This you will get. See how we do multiplication. This row with this column will be a first. Then this with this second. And this with this third. Okay. Dotted with 1 0 0. What you will get? A only. Okay.
Okay, sir.
Got it? So change in length along EX direction is A. Second part they said along EY direction. So now your N becomes EY. So again we will multiply our strain matrix. Zero 1 0 0 1 0. Yeah. Hello. Your mic is muted.
सर ये EX 100 और EY 010 सर ये कहाँ से आ जा रहा है?
As per our coordinate system we have this thing na EX, EY and EZ.
Yes, sir.
So we'll define all the things in respect to these three only vectors.
Okay, sir.
So if only Ex is given, so it is 1 0 0. If Ey is there,
0 1 0.
if Z is there,
Yes,
okay.
sir. Yes, sir. Yes.
If somewhere, suppose if it is given like this, which is in the third part, I'll show you. Okay. So this is the, if you multiply for change in length for Ey direction, along Ey direction, multiply. This you will multiply first. Okay.
Yes, sir.
What you will get?
0
A by 2.
A by 2.
This with this. This with this.
With this. Yes, sir.
So A by 2. Second, this with this.
This with this. Yes, sir.
So 0
0
0
0
0 1 0. Okay. So dot product, it will be 0.
0 हो जाएगा, sir.
Okay. Now in third part,
EZ.
they said along EY and EZ. This two. 1 second, I will check the question also.
Yes, sir. Why?
Yeah, EX and EY.
1 by root 2.
So it's EX and EY. EX and EY. So this will be written as this 1 by root 2, 1 by root 2, 0. Okay. So again we'll do change in length is epsilon n dotted with n. Our n is this.
Yes, sir.
So again we'll write A by 2, 0, A by 2, 0, 0. 1 by root 2, 1 by root 2, 0. 1 by root 2, 1 by root 2, 0. Correct? We'll multiply this two first.
Yes, sir.
So what we'll get?
A upon root 2.
A by root 2 plus A by 2 root 2.
A by 2 root 2. 0.
Here A by 2 root 2. See this with this.
Yes, sir. Yes, sir.
And last is 0.
0.
This is 1 by root 2. 1 by root 2. 0. So what we'll get? A by 2 plus A upon 2 into 2
into 2
plus A by 2 into 2. Got it? No. Dot product is there, na?
Yes, sir. Got it. Got it.
Got it? Root 2 multiplied by root 2 is 2 only.
2. Yes, sir.
So what will become? A by 2 plus A by 4 plus A by 4.
Plus A by 4.
Which is nothing but A.
Yes, sir.
Got it?
Yes, sir.
So you can calculate change in length. But these things we are doing because we know the deformation is small. Okay. Just make sure. Okay, this thing. When deformation are large, you have to use this formula. Okay. Where C is calculated with the help of this thing. Okay. Got it? So now we'll go ahead with change in angle. Okay. Change in angle. Okay. So change in angle is cos of theta reference. Is nothing but okay, this is the formula for large deformations. Okay.
Large deformation का.
See, you can use this formula for small also. Okay, whatever you are using for large, you can use for small. But since it's small, you can do some simpler calculations. You can use for simpler thing. Okay. You can make this equation simple with the help by knowing the deformation is small. So why you use this complex equation for small? Okay. Getting my point?
Yes, sir.
See, this formula you have to calculate C with old method. Then you have to put in the formula. So if the deformation is small, we just make this equation little bit simpler. Okay. This is the theta reference, cos theta reference for this thing, and change in angle is theta current. Sorry, I have written wrong. This is theta current. Sorry. Okay. So change in angle is theta current minus theta reference, which is equal to delta theta. Okay. What is theta reference? So theta reference is cos theta reference is nothing but A dotted with B. This is the dot. This thing you know.
Yes,
Dot
sir.
product. So this is theta reference. Here from this you will calculate theta reference, and from this formula you will calculate theta current. Okay. So now for small deformation, this cos theta current is nothing but 2 epsilon A dotted with B upon sin theta reference. Okay. And theta reference you will find from this formula only. Okay. So now in our question, we'll go to question. See, E part. Using the linearized material strain, calculate the exact change in the angle between two line segments oriented along EX and EY. So in the reference configuration. Okay. They wanted to ask what is the angle change when the lines are oriented along EX and EY direction. Okay. So now here, given in the question A as EX, okay, and B as EY, it's given in the question, okay. Epsilon you know already, A by 2, 0, A by 2, 0, 0, okay. So now first we'll calculate theta ref. So cos theta ref is nothing but A dotted with B, EX dotted with EY upon mod of A and mod of B. Tell me what is this thing first thing? EX dotted with EY. Is nothing but 0. See, I told you in the very first problem session that conical delta ij, which is equal to 1 and 0 when I is equal to j and when I is not equal to j.
Yes, sir.
It comes with dot product A dotted with B, which is equal to AI Bj delta ij. Got it?
Yes,
So
sir.
here I is not equal to j. So that is equal to 0. So theta ref will be equal to 90 degree or pi by 2. Okay. Then sin theta ref will be 1. Sin 90 degree is 1. So our 1 second. This is change in angle. Okay. Sorry for the mistake. This is change in angle. Delta theta only. Okay. So delta theta becomes, from this equation, sin theta ref is 1. So it becomes 2 epsilon A dotted with B. Okay. So now we'll put the thing in the formula.
Theta reference is equal to 0 and sin theta reference is equal to 1.
Okay. What is A? EX 1 0 0. And what is B? EY 0 1 0.
0 1 0.
So now we'll do. It becomes 2A. It becomes A 0. Got it? How I got this thing? First we'll multiply this thing.
Yes, sir.
So what is this? A. So change in angle is nothing but A. Okay.
Yes, sir.
Got it? So now 2-3 questions more. Till now you understood what we have found out. See, from the given motion field, with what we have found out, F, deformation gradient. Okay, we have found out U capital X, displacement gradient. Okay, what we have found out, C, which is nothing but F transpose F, or 1 plus 2 epsilon. Okay, we have seen epsilon M, materialized linearized strain, and spatial linearized strain are equal, which is nothing but half of H plus H transpose, which is equal to half of small h plus
small transpose.
capital H is nothing but F minus I, and small h is equal to 1 minus F inverse, or capital H is equal to dou U capital X by dou capital X.
Yes, sir.
Small h is equal to dou
Small x minus d small x.
Okay. Then we see stretch ratio. Lambda, which is nothing but under root of C n dotted with n, or lambda n minus 1 is equal to epsilon n dotted with n. This is nothing but change in length. Got it?
Yes, sir.
This we use when deformations are small. Okay. Then we see angle change. Delta theta is equal to 2 epsilon A dotted with B upon sin theta reference. Okay. And cos theta reference is nothing but A dotted with B upon magnitude of A, magnitude of B. This is also for small deformation. Okay. Understood so far? These things we have seen in the example form. Okay. Not 2-3 things more I have to tell you. Okay. So when will you say, like, if someone asks you, can the deformation be classified as small deformation, when you will say? When you will say this thing? When h is equal to small h, you can say this thing?
Yes, sir.
So this is the answer. Okay. Check. Okay. When both are equal, you classify the deformation as small deformation. Okay. Type of motion field. Okay. To answer this question, first find out f. So what is our f? 1 plus a 0 0 a 1 0 0 0 1. This is our f. Okay. So this f doesn't consist any x y z term. The f doesn't have any x, y or z variable. All are constant. No. See, this term is constant. No x and y are involved.
Yes,
This
sir.
is constant. This 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 is constant, and this is constant. All terms are independent of x, y, z. So
Yes, sir.
what we call this as constant. F is constant. Okay. So this type of motion is known as homogeneous deformation field. Okay. Okay. if any one element has x or y or z, suppose this is there, for example, so this is inhomogeneous, okay, because x is there, okay. Or suppose y has been given, that is also same, okay.
Yes, sir.
Or z is given, that is also same, anywhere here or here they have given x, y. So it should be free from all the x, y, z term to be called as homogeneous deformation field, okay. Got it? If someone asks in the question what is the type of deformation field, just check the F matrix, okay. Last question. Suppose someone has given you this equation. This equation is in reference form. This is the equation of circle.
Mx square plus c.
Mx square plus c, no. X square plus y square.
Mx.
Mx plus c is a straight line equation, no.
Okay, sir.
This is a equation of circle of center 0 and radius 2. If I draw this thing, this circle will be like this. This radius will be 2. Okay, and center is 0, 0. So this is in reference form. So someone will ask you what is the shape in spatial form. Okay. So deformation has been given to you know this thing. X is small y is equal to capital Y plus a capital X, and small z is given to you, small z is equal to capital Z. So just shift the value here. Okay.
Okay, sir.
So what is capital X? Is nothing but 1 upon 1 plus a into small x. What is capital Y? Is nothing but small y minus a upon 1 plus a into small x. And capital Z is nothing but small z. So this equation can be changed to plus we can write like this.
Yes, sir.
Or this is in spatial form. Okay. Now open this thing. X square upon 1 plus a square.
Yes, sir.
Plus y square.
Minus ax
Plus a upon 1 plus a whole square is x square.
Yes, sir.
Minus 2a upon 1 plus a xy equal to 4. No, one more term is there. No. Okay, all terms are there. Okay. So just take here all these things. It will become 1 plus a square upon 1 plus a whole square. I will write in that variable. Okay. Plus y square. One second. I will write like this. Minus 2a upon 1 plus a xy plus y square.
Yes, sir.
Is equal to 4. Now tell me what is the shape of this form. How will you say?
Ax square plus bx plus c.
See, the general form is to tell whether the equation is circle, ellipse or hyperbola is okay. Suppose the equation is in the form this. Okay. So you just have to calculate b square minus 4ac. Okay.
Yes, sir.
If it's less than 0, it is ellipse. If it's greater than 0, it is hyperbola.
Hyperbola.
And if b is equal to 0 and a is equal to c, it is circle. Okay.
Okay, sir.
Now we'll check with our equation. A is equal to this a from our side. 1 plus a square upon 1 plus a square whole square.
Yes, sir.
What is B?
B
Minus 2a upon 1 plus a. And what is C? 1. Okay. So from here, B is not equal to 0. So see, you have this circle in your reference form. Okay. And with the change of deformation field, it doesn't remain circle. Okay. It changes its shape. You got it this point?
Yes, sir.
So now B is not equal to 0, so it's not a circle. Now calculate B square minus 4AC.
4AC.
It's nothing but 4A square 1 plus A square minus 4 1 plus A square upon 1 plus A square.
A square into
This is nothing but minus 4 upon 1 plus A square. So see, this term will always be greater than 0 because square is there. 4 is greater than 0 and negative is there. So it will be always less than 0. So B square minus 4AC is less than 0. So what it is called? Ellipse. So your shape becomes ellipse. So circle is in reference form. And ellipse it becomes in current form. Got it? So this is what I have covered in problem solving section of week 4. So almost I have covered all the points and all the things which are required in the week 4 assignment also.
सर
Yeah.
अगर एक असाइनमेंट में क्वेश्चन पूछा है ई एक्स एक्स कंपोनेंट
Yeah. EXX और CXX.
नहीं उसको क्या कहते हैं सर वेट अ मिनट हाँ सी एक्स एक्स है फिर वो उसको टाउ कहते सिग्मा वाई वाई
C. I'll show you one thing. C. Here. C matrix is nothing but F transpose F.
Yes, sir.
Or 1 plus 2 epsilon. So we will get some matrix. This is nothing but CXX, CXY, CXZ, CXY, CYY, YZ. Okay, CXZ, CYZ, CZZ. So just calculate the matrix and whatever the coefficient is there, you write that thing. Okay.
Okay.
Got it. Similarly for epsilon also. Half of H plus H transpose we write. So the matrix we got will become epsilon. Epsilon XX.
Epsilon.
XY epsilon XZ. Epsilon XY. YY epsilon YZ. XZ epsilon YZ. Epsilon ZZ. Okay. So just write the coefficients there, whatever asked.
Okay, sir.
Any other doubt?
No, sir.
Okay. One more thing I am missing this that. See, if this is the matrix of epsilon, this is the matrix you will get for strain. So all the diagonal terms in strain matrix are referred to as change in length.
Change in length.
Yes. So if someone asks what is the change in length in EX direction? EX direction. It is nothing but epsilon XX. Okay. Change in length in EY direction. It is nothing but epsilon YY.
YY.
And EZ direction is nothing but
epsilon Z.
Epsilon ZZ. And all the non-diagonal terms like this. Different color I will use. Is nothing but half of delta theta, angle change. Okay.
Okay, sir.
If someone asks what is the angle change in EX, EY direction, that EX and EZ direction, EY direction, sorry, angle change, is nothing but what? twice of epsilon xy. Okay. In EY and EZ direction is nothing but twice into, this is into sign, okay, don't confuse, YZ, okay, got it? So right up to here, okay, so this is what I have covered in this problem solving session 4, which basically covered all the topics in week 4 lectures, and I have solved one numerical problem and gave the hands-on experience on calculating how to calculate deformation gradient, how to calculate deformation gradient, displacement gradient, how to calculate right Cauchy green deformation tensor, how to compute linearized strain in both the material and spatial form. If our deformation is very small, then material linearized strain and spatial linearized strain are same. Finally, we see how to calculate change in length and change in angle. Okay. So this is what from this live session. If you have any doubt, please feel free to question.
No, sir.
So all things are cleared. I hope it will help you in week 4 assignment. Okay. Any feedback for today's lecture?
Excellent.
Thanks too. Okay, then we'll wrap up the session. Okay, thank you. Thank you for joining.